Welcome to the fourth video where we will look into unit root tests and derive the limiting distribution of the test statistic in our random walk model. Now we start from the DGP, where we have a random walk model without drift and an initial condition y not equal to 0, such that we can alternatively express yt as the partial sum of our first t error terms. And we would now like to estimate this model where we regress y on its lagged value and our error term is et in our estimated model. The unit root test would then test the null hypothesis that rho is equal to 1. So under the null, we have a unit root and the alternative is a stationary rho. Let us now determine the limiting distribution of our test statistic under the null of a unit root. And in the derivations, we will often make use of, let's say, the DGP, which I will always indicate in blue. And we will also need the details of the models that we will estimate, which I will always indicate in red on the next couple of slides. Now we know that we need to start from the least squares estimator in our model that we want to estimate. And it should be very easy by now to write down this expression for the least squares estimator, where we have x prime x inverse. Here in this case, the sum of the squared lags in the denominator, and the term x prime y in the numerator, which is here the cross product of the lagged value of y and itself. What is our key next step? Well, we plug in the expression for the DGP indicated in blue, where yt is nothing more than yt minus 1 plus our IID error. And we can then simply expand this product over here, where we see that the first term cancels out with the denominator, such that we can immediately bring the value 1 to the left-hand side. And for the second term in parentheses, we are left with the cross product of yt minus 1 and our error term epsilon t. In the next step, we then need to determine the appropriate scaling, or the asymptotic rate of convergence, or in other words, the power of t by which we need to blow up this difference at the left-hand side. And for this, we will develop the numerator, this guy over here, and the denominator, this guy over here, separately, each time introducing the appropriate scaling for numerator and denominator. And then we will combine the powers of t that we need there to, of course, also accordingly multiply the left-hand side by the resulting power of t. Let's start with the denominator. Let's start with the numerator, that guy over here. So we have our numerator, and we will rewrite the numerator in such a way that we end up with expressions only involving partial sums of the error terms. Why? Well, because we know how to relate these to our scaled partial sum process, for which we can apply the functional central limit theorem. So let us start from the DGP, which is nothing more than the sum of the lagged value of y and the error term. And if we now square the DGP, we see that if we expand the terms, the cross product of yt minus 1 and the error already pops up. Now, after simply bringing this squared term to the left-hand side, we arrive at this expression over here. Now, in the numerator, we actually have a sum of this cross product term popping up, namely a sum from t1 up until capital T. And so I can also take the sum from t equals to 1 up until capital T at both this left-hand side and the right-hand side, which I do over here in this line. Now, how does our left-hand side simplify further? Well, you will see if you write it out completely that this is a so-called telescopic sum, where all consecutive terms will cancel out with each other apart from the last one at time point capital T and the initial one at time point t equals 0. So you're only left with this difference. And that is exactly the same trick as we saw last week in the computations with the Beveridge-Nelson decomposition. So please verify that for yourself. Now we arrived already at this expression where we clearly recognize our numerator popping up as indicated in this box. Now on the next slide, I just rewrite this expression such that I have my numerator, so the box popping up on the left-hand side. So that means that I bring my sum of the error terms, this guy over here, to the other side. And I also have a factor 1/2 popping up since I had, the factor 2 in front of the box on the previous slide. Remember, our goal is to express the numerator, so the box, in terms of partial sums of the errors only. So we already have one sum of the error terms, the second term here in the parentheses. But we also would like to rewrite these guys, so the first term over here, as a sum of the errors. Now for why not, our job is easy. We can simply drop it, since we will always assume that this is 0. How can we rewrite y capital T squared as a partial sum of the errors? Well, remember, under the DGP, again, given in blue, we can rewrite any value of y, so also y at time point capital T, as the sum of the errors from t equals to 1 up until that same time point, again, capital T in this case. So plugging this in over here, that brought us then to this expression where we have rewritten the numerator as a function of partial sums of the errors only. And from here onwards, we can relate to our scaled partial sum process and apply the functional central limit theorem. Now, in order to arrive at our scaled partial sum, we need to introduce the appropriate scaling on this term. And so we need the appropriate scaling on this guy. We need appropriate scaling on this guy. Now, let us start with the second term over here, which is the easy one from the IID world. We know that if we have a factor 1/capital T in front of it, then by the law of large numbers, this guy converges to the expected value of the squared errors, which is sigma squared. So for the second term, we would need scaling by 1/capital T. What do we need for the first term? Well, the first term over here. Well, we know that this is the partial sum for r equal to 1, which is nothing more than this guy over here that pops up in our numerator with a factor actually 1/√t in front of it. And then we indeed sum up all of the observations, and r is equal to 1, or we sum up all observations up until time point capital T. And we know that this guy goes to a standard Brownian motion W1 scaled by a factor sigma. Now, by the continuous mapping theorem, we know that if we simply square this guy to the left, then the convergence in distribution is maintained if we also square, let's say, the guy at the right-hand side over here. So putting all of these pieces together, we need that the numerator needs to be divided by t. So we need to have a factor 1 over t, because then we have the convergence results, which we can make use of from the previous slide. And I just copied them over here. Now, a couple of remarks about this limiting distribution. First, this guy over here is nothing more than a standard normal distribution. And we know that the square of a standard normal is distributed like a chi-squared distribution with 1 degree of freedom. Now, secondly, what is the expected value of our limiting distribution? Well, the expected value of a chi-square with 1 degree of freedom is equal to 1. So the expected value of this limiting distribution is then 1 minus 1, or equal to 0. Third question, is the limiting distribution symmetric? Well, no, because the chi-square is not a symmetric distribution, it's asymmetric. And then the last question, what would be the difference with stationary asymptotics? We'll have a look again at the question from your tutorial last week. There you found that this guy, this cross product, had to be divided by root t. So it requires scaling by root t, and then it converges to a normal distribution. So last week you needed root t, here you need 1 over t, and also the limiting distributions are very different. So quite some differences between the non-stationary and the stationary asymptotics. Now, to put all pieces in place, I took here a rather long route to arrive at the limiting distribution of the numerator. But you can actually also derive the same results in a faster way through an alternative route, which you will explore in the tutorial. Now let us continue with the denominator, and remember the denominator was nothing more than the sum of the squared lag. Also for this term, we would like to rewrite it in a form of a partial sum of the errors. And remember from the DGP that yt can be rewritten as the partial sum of the errors up until time point t, the same time point. So let's plug this into our expression for the denominator over here. Now, how can we relate this sum of the errors to our partial sum process? Well, remember, our scaled partial sum process for fixed R, fraction of the sample over which you sum, is defined like this. So what is the fraction of the sample over which we sum in this case? Well, we sum just the first t minus 1 observations out of the entire sample of length capital T. And this sum of the errors is exactly what is popping up in our denominator, apart from the factor 1 over root t, of course. So if we bring this to the left-hand side, then we have root t times our scaled partial sum process for R equal to t minus 1 over capital T. And I can take this factor root t outside of the square if I square it, of course. And then I'm only left with this expression over here. So we arrived already at this expression for the denominator. And let's copy this guy over to the next slide such that we can continue. So I copy over this guy over here. Now, what are the sums of our partial sum process over here? Well, remember, this is a piecewise constant function over intervals of length 1 over capital T. And I've recopied here a visual example on the slide. On the horizontal axis, I have R going from 0 up until 1 in intervals of length 1 over T. On the vertical axis, I have the value of the scaled partial sum process. Now let's zoom into the interval between r equal to t minus 1 over capital T and t over capital T. Now the function value at r equal to t minus 1 over capital T is this point over here, indicated also on the vertical axis. And if we would like to compute the surface of this area under the curve, we would be getting the function value at r equal to t minus 1 over capital T multiplied by the length of this interval, which is just 1 over capital T. And that gives this area over here, this guy. Now we also know that this area under the curve is equal to, or is nothing more than the integral of our scaled partial sum process from r equal to t minus 1 over capital T, this point up until t over capital T. So we've computed this area under the curve in two different ways. First way, and this is also our integral. Now this equation in red, I've rewritten here on the slide. So this guy over here is just this equation from the previous slide where I just brought the capital T to the other side here. Okay, so actually you see that I have squared, I've taken the square of xt, but this also the square of xt is piecewise constant. You just need to take the square of the values on the vertical axis and then everything goes through. Now, if we finally need to sum up all of these areas under the curve, namely from t equals to 1 up until capital T, or alternatively, we just need to sum up these integrals from r equal to 0 up until 1. And we're just left with this expression over here. Okay, so I already managed to rewrite the denominator in this form. By which power of t should we now scale for this to converge in distribution? What are the ingredients that we know? We know that our partial sum process goes to this Brownian motion under the functional central limit theorem. Now we don't actually have this popping up, but we have a transformation under a continuous function g, so we can rely on the continuous mapping theorem. This integral of the square will also converge in distribution to the same integral of the square over here. Of course, we don't have this term in red, but it's blown up by t squared. So if we would divide by c squared, we would exactly get the red term. And we know that this guy converges to this expression over here by the functional central limit theorem and the continuous mapping theorem. And one good advice, don't forget the sigma squared, because it's the scaled partial sum that goes to our Brownian motion, but we just have the partial sum popping up. So our sigma squared will always, or will often pop up also in front of the Brownian motion then. Now in your tutorial, you will also look at an alternative, faster way to arrive at these solutions by recognizing a Riemann sum. And to get you started, I've put some initial hints here on this slide, which might be useful. So have a look at this slide to get you started on the assignment. Now, what have we done? We've developed the numerator and the denominator separately, and we are ready to put all pieces together to determine the appropriate rate of convergence for this guy over here. Remember, the numerator needed scaling by 1 over t to converge in distribution. The denominator needed scaling by 1 over t squared in order to converge in distribution. So I have here a 1 over t for the numerator. I have a 1 over t squared for the denominator, Or alternatively, what did I do? I blew up the right-hand side by t. And so, of course, that I also need to do at the left-hand side. And so the appropriate asymptotic rate of convergence is t. In order to arrive at the limiting distribution of this guy, where I then just copied over the limiting distribution of the numerator and the one from the denominator, where you then just see that the terms with the sigma squared cancel out. So the asymptotic rate of convergence t is actually faster than in stationary asymptotics, which was root t. And the limiting distribution that we get is the so-called Dickey-Fuller distribution. So how can we do inference based on this limiting distribution? Well, here on the slide, you see a histogram of 100,000 realizations of this distribution. In practice, you can take the alpha quantile for a test of size alpha. And if the value of the test statistic, which is nothing more than this guy over here, this is the value of the test statistic, the sample size times the estimate of rho minus 1. Well, if the value of the test statistic falls below the critical value, so it's more extreme than a critical value, then you reject the null hypothesis. Otherwise, you do not reject the null. Now, while t times rho hat minus 1 acts as a test statistic on its own for the unit root test, you can, of course, also still compute your regular t statistic that you know from the regression courses. As usual, this regular t statistic is nothing more than our estimator minus the value under the null, which is 1, divided by the usual OLS standard error of our estimated coefficient. Now, if you rearrange the terms a bit, and if you plug in the expression for the sample variance of the residuals, you see that you are actually left with expressions for terms that you recognize from before, whose limiting distributions you also derived already. In addition, the sample variance of the residuals, this guy over here, goes also to sigma squared, since the consistency of rho hat implies that this guy converges in probability to sigma squared. If you then plug in all of the pieces, the expressions you derived on the previous slides, and the convergence of the sample variance, you also arrive at the limiting distribution of this t statistic